Okay, here is a lesson on Kirchhoff's laws. I hope I've spelt that correctly. It's a little bit extra to the syllabus, but it's a really useful way to work out complex circuits. What I'm going to do is build this up and show you why it works, and then show you the quick technique a little later on. So let's build a first circuit, and hoping that you have done resistor combinations, then we should be able to hopefully solve this circuit and the currents flowing in this circuit. Let's put some values to the resistors. Let's give this 10 ohm resistance. Let's give this one a 20 ohm resistance, and finally this one a 40 ohm resistance. Fantastic. Now what we're going to do is, with a 10 volt battery placed in, I'm looking at the currents which are being formed here. Let's call this I1. This one is going to be I2, and this one flowing down there is I3. So how are we going to work that out? Well, hopefully you can see that these are in a parallel combination, and this is series to this parallel combination. So if we worked out, if I redrew it, for instance, maybe this might make life a little easier. If I redrew it as, might get a little cramped, but that might make life a little simpler. We can work out, of course, let me just write in those values. Of course, we can work out fairly easily our overall current by working out our effective resistance. So let's look at these two together. What's their total resistance? Well, if you remember with this relationship for resistors in parallel, that can actually we could do it this way, or it can be simplified for two, and just for two resistors. This is the product of them over their addition. And in this instance, that should be quite straightforward, because we have 20 by 40 over 20 plus 40, giving us 80 over 60, giving us, what's that? That's about 80 over 60 gives us oh wait a minute, 800, sorry, over 60. 8 over 6 gives us approximately, in actual fact, I'll use the calculator because numbers, precision here will matter, about 13.3 ohms. Okay, now we have a 13.3 ohm in series with a 10 ohm, so therefore our total resistance presented to us is going to be the 10 ohm plus the 13.3 ohm, as if this were in series with this effective resistance. Giving a total of, not too difficult there, 23.3 ohms. Good. Now, what happens is that which is coming out of the battery feels the resistance of both of those put together, so we can say that the current, 1, is going to be the EMF of the battery, 10, divided by the total resistance, 10 over 23.3, giving us about 0.429 amps. Excellent. Now you can probably see and appreciate here that if I've got twice the resistance here on this lower path on I3 than I2, then I will simply have a nice split of 2/3 go this way and 1/3 go this way. So let's just work that out then. So I2 is going to be 2/3 of the total current, which gives us 0.286, and I3, which has the higher resistance, will take a value of 1/3 of the 0.429 amps, or the difference, which gives us 0.429 divided by 3, 0.143 amps. Great, okay, so that's the first stage. Now I'm going to draw another circuit which isn't that dissimilar but this time I'm going to move the source of the battery. So we're going to have the same setup as before. This time no battery there. And I'm going to place a battery on this side. But all the same resistors are staying present. So we have our 10 ohm, our 40 ohm, our 20 ohm. And this will be running at 20 volts. So what I'd like us to do again is work out these these currents. I'll describe this one here as I1, I2, and I3. I'll explain why I've put that one as I2 and that's as I1 later, because I'm trying to combine these currents later. But for the meanwhile, let's see if we can do exactly what we did in the first instance. We're going to say that we have two in parallel with each other, this combination here, 10 and 40. That is in series with the 20 ohm. I haven't drawn that too clearly, but I hope you understand what we're doing. And I've got 20 volts coming through. So what's the effective resistance of these two? Remember this shortcut. We said that the total resistance of a parallel circuit is going to be the product of the two over the addition, which leaves us with 10 by 40 divided by 10 plus 40. 400 over 50, which leaves us with 8 ohms effectively. There's my effective resistance of those two. So now, what the total resistance does this battery feel, or I2? Well, my new total resistance is going to be 8 plus the 20, giving me 28 ohms. That's what it's felt by the battery. So my current will be the voltage divided by the total resistance, 20 over 28, leaving me with, numbers, precision is important here, 0.714 amps. Now, once again, this is splitting, of course, I1 and I3. And because I know I've got 4 times more resistance here than there, it must suggest 1/5 comes down here and 4/5 go through there. So, quite simply, I1 is going to be 4/5 of the total current, giving me 0.571 amps, and I3, a bit coming down here, will be 1/5 of the total, and that gives me a current of 0.143 amps. Superb. So both ways, I've done both things, but I've done it with different batteries. Now, the magic of this circuit is, with these two circuits, and I'm actually going to lie them over each other, is that I can superimpose those circuits over each other. So whatever current I discovered here, I1, I2, I3, I can add them to the currents I found here, I1, I2, I3, and work out how this much more complicated circuit takes hold. So let me draw the complicated circuit that we're after. The complicated circuit is, I have my 10 volt battery with 10 ohms, 40 ohms, 20 ohms, and a 20 volt battery here. And I'm going to label these up as I1, I2, and I3. Now, the wonder of Kirchhoff, well, should we say first of all, let's just work out from the previous example what those values ought to be. In my previous one, I had 0.429 and 0.571. So I had, for I1, I had 0.429 going in this direction, and I had 0.571 going in this direction. So that must leave me with a total of, going in this direction, the difference. Because these are vectors, they get to add together and subtract away. 0.142 amps. What's going to take place with I2? I2, we have, let's just take a look here. I had moving towards the right 0.286 and moving to the left I2 was 0.714, leaving me with, to the left, the difference. .428 amps. And finally with I3, they're both moving downwards, and we had 0.143 and, believe it or not, 0.143, giving me a grand total of 0.286 amps. Now that's a pretty long-winded way of doing it, but the idea of superimposing this circuit onto that circuit actually is, I hope, quite intuitive and something you can do. But Kirchhoff has a much better way of dealing with it. Kirchhoff has two laws. First is the Kirchhoff current law, and that says that the sum of the currents into a junction will all equal 0. I think that's how he says it. But really what I'd like to say is that the currents coming into, so currents coming into a junction will equal the currents coming out of the junction. Those coming into the point will equal that coming out of the point. Kirchhoff current law. Also, Kirchhoff voltage law, KVL, suggests that in any enclosed loop, the sum of the voltages by each of these equals 0. Sum of the EMFs equals 0. Or I'd like to say the 10 volts from the battery in this circuit will equal that deposited on the first resistor, 10I1, because V equals IR, so I times R is your V, plus 40I3. And this holds for any loop. It could be this loop, it could be this loop, or even it could be right round the outside loop. Any of those loops. I'm going to call this 1 and that 2. So let's see if that makes sense then. That was for my first loop, and we'll see whether Kirchhoff's rule comes out with what we've done before superimposed. And let's try number 2. 20 volts must equal 20 I2 plus, because I've gone this way, coming back round 40 I3. Good, so now it's just a set of simultaneous equations that I need to solve. Right, what am I going to do first of all? Let's minus 1 from 2, and that should give me, get rid of this part, so that gives me minus 10 volts equals minus 10 I1 plus 10 I1 minus 20 I2. Good, I can actually, let's divide through and make this a lot easier. In other words, let's say First of all, let's change these into the other way around. 20i2 minus 10i1 equals 10. 1 equals 2i1, minus i1. I could then do the same with number 1. So let's take number 1 to one side. Let's divide through by 10, so it gives me 1 equals I1 plus 4 I3. If we add these two together, then we'll see the I1 term fall out. So let's add those two together. So this and that, add 1, and let's call it 2 dash plus 2 dash. And that leaves me with 2 equals we'll come around in a circle, hold on. Let's just hold fire there a minute. Let's convert this, I didn't see that, into 4 I1 plus I2 because of this rule at the top. Giving me 1 is 5 I1 plus 4 I2. Yeah, I didn't think it was going to be that easy. Goodness me, I should have just come out with the answers here for you rather than trawl you through all of this. But nonetheless, let's give this a go. So let's take I1 from here. I1 is 1, 2, I2 minus 1. Let's plug that into the previous one for I1 up here. So 1 equals 5. 2 I2 minus 1 plus 4 I2. So I'm taking this and I'm substituting it into this, which gives me, which is the same as 10 I2 minus 5 plus 4 I2. 14 I2 minus 5 equals 1. So I2 is 6 over 14, giving me 0.429 amps. Is that right? 429 I2, that's correct, and it's going in that direction which is positive. Check. I1 was simply 2i2 minus 1, giving me 2 lots of 0.429 minus 1, giving us minus 0.143 amps. The minus implies, first of all, yes, it is correct if we look at the top, but this time it's going in that direction, which implies that my I1, yes, must be minus, because I thought it was going in that direction, so minus implies that direction. Excellent. And finally, I3, it's going to be the addition of the two, 0.429 plus minus 0.143. I nearly thought I'd got it wrong there, but that should be 0.286 amps. Excellent. Tick, tick, tick. They all correlate with these three right at the top. So a simple method of being able to do more complicated circuits. For a much simpler circuit, and then superimpose the two circuits. That shows it's working, and or work Kirchhoff's law out. Right, I'm going to give you one more, which hopefully will be simpler, a little bit quicker too, and just to practice. So what do we have here? We have a simple circuit of 12 volts. Let's wrong side. Let's start again. 12 volts down here. and 5 volts. I hope you can see that. Specify I2, I1 like before, and I3 of 4 ohms, 3 ohms, and 2 ohms. So it's very simply, what are the 3 kinds? If you think you know the answer, hit pause and give it a go, otherwise here comes the answers. Right, I'm going to consider these 2 loops, 1 and 2. For loop 1, I have 12, using Kirchhoff's current voltage law, is going to be I3, 4 lots in it. Then I come round here with I1 plus 3I1. For loop 2, I get 5 is coming around here 4I3 plus 2I2. I2 comes around here, this goes into I2. That goes into I1. Right, let's get rid of this term. So it gives me 3I1 minus 2I2 gives me 7. Also, I'm going to plug in my, if that was the Kirchhoff voltage law, my Kirchhoff current law, which is I1 plus I2 is I3. So therefore, if I take one of those, 5 equals 4 I1 plus I2 plus 2I2. 5 is 4 I1 plus 4 lots plus 2 lots, 6 I2. Let's try and combine these two together somehow. Not easy, but I'm going to multiply everything by 2 on this one. 14 is equal to... No, that doesn't work. Hold on. I'm looking for I2, so let's get 3 of this lot. So 21, let's multiply by 3, is 9I1 minus 6I2. Line that up with 5, which is 4I1 plus 6I2. Add them together. 26 equals 13I1. I1 equals 26 over 13, which is 2 amps. Good. I2 is going to be, let's take one of these up here. 5 minus 4I1 over 6. 5 minus 4 by 2 over 6 gives me minus 3 over 6, which is minus 0.5. You can see that. 2, leaving me with an addition of 1.5 amps, which is I3. Good. I hope that all makes sense.